Hi, I'm Conlon Foster, and this is my ENME351 project lab on the reverse rotation effect, the wagon wheel effect, or most accurately, the stroboscopic effect. When an object, such as a wagon wheel, rotates at a high enough rotational velocity, aliasing occurs. Our eyes can only register so many frames per second. For a wagon wheel, there are relationships between the number of spokes and revolutions per second that can cause it to appear stationary or rotate backwards. I used an image from my old Physics 3 class in which we have a wagon wheel with two different sets of spokes. Depending on the rotational velocity it goes at, it will appear as if both two sets of spokes are rotating in different directions.
When it came time to construct this project, I thought to myself, what is more fitting to a lab focused around something I learned in Physics 3 than light? In my circuit, I'm using a photoresistor as a sensor. It measures the light intensity shining down upon it to enact a relative resistance that allows for a fractional voltage to pass through. My Arduino supplies 5 volts, so in the brightest possible scenario, the photoresistor will allow almost 5 volts. The darker the light intensity gets, the smaller the voltage that passes through. I constructed an LED purely to demonstrate this response. I then measured this voltage using my Arduino sketch and use it to actuate a stepper motor. The motor rotates relative to the amount of light shining down on the photoresistor. The brighter the light, the faster the motor will spin. The Arduino sketch shows how I used my stepper code from a previous lab and made its speed a function of the voltage passing through the resistor. I tried a variety of different size wagon wheels before deciding on the 0.875-inch diameter one that I thought best worked for my video.
With this wagon wheel attached to the stepper motor, it's time to begin. Here, I'll demonstrate the rotational speed of the stepper motor when the photoresistor allows a small measured voltage of 2.0. And now, under a brighter circumstance where the voltage is 4.80, we can see that it rotates faster. Theoretically, if we had a large enough voltage and a higher rated stepper motor, we could enact the stroboscopic effect. But while we can't see it physically in this scenario, I had an idea.
To simulate a higher rotational speed, I took 2 video clips, one with less light intensity and one with more, and sped them up. In this dimmer clip, the photoresistor allowed through 3.28 volts, and when I increased the speed to 32 times playback, I found a rotational speed at which the alternating rotation occurs. If this is difficult to see, I suggest looking at the top of the wheel. When I allowed more light through, I only had to speed up the video by 20 times to achieve a similar rotational speed. This shows that the occurrence of the stroboscopic effect is a function of rotational speed. Aliasing occurs both in our videos and in our eyes, as this playback is capped at 30 frames per second, whereas a total of 13 spokes rotated over 3 revolutions per second. In order to better display this phenomenon, I created a processing sketch to vary the rotational speed of the wagon wheel with the voltage allowed through the photoresistor. I created a second Arduino sketch with no stepper controls, as the delays interfered with the rotational speed. I instead controlled the process in processing. A delay of 90 milliseconds was the smallest delay I could get with the processing sketch, which varied the voltage as a fraction of 5. These numbers, while seemingly arbitrary, were chosen because they demonstrate how, with little light sense, the actuating stepper motor may not spin fast enough to enact the stroboscopic effect, whereas when light intensity is increased, the effect plainly occurs. The code for everything is available upon request. Thank you for watching my project lab.